I'm Krishna Baride, and I'm excited to be here today to talk about how we transform our PLM product lifecycle management systems using Go programming language. Modern product development demands a lot from PLM systems. They need to handle massive amount of data and provide insights in real time. Our journey revolutionized concurrency and a microservices architecture. In this presentation, I'll walk you through how we built a system that processes over 100,000 product data points per second across the distributed services. This resulted in a reduction in product launch timelines processing. We'll cover everything from the custom schedulers, circuit breakers, to memory optimization and high throughput pipelines. I'll share the architectural decisions that helped us transform our PLM infrastructure into a high performance AI driven platform. So let's start by understanding the challenges that we face. As you can see here, we were dealing with some real time, first of all, massive data volume. PLM systems struggle with the sheer volume of product data generated in today's development environments. Think about CAD files, specifications, test results, and regulatory documentation. It creates a huge processing demand. Legacy PLM architecture often rely on monolithic databases and sequential processing pipelines. These simply cannot scale to meet the demands of increased product complexity and data requirements. Third, the cross-team communication. Information silos between different teams, engineering, manufacturing, quality, causes significant delays. Critical data is often trapped in disparate systems and formats, making it more and more difficult to share and collaborate effectively. To address these challenges, we built a clear engine for CAD. This engine is really the foundation of injection and transformation that feeds all our downstream systems. It has three key components. First is the metadata extraction. Specialized parser converts proprietary CAD format into standardized for seamless integration with analysis systems and visualization tools. Secondly, the parallel processing. We use Go routines to process different sections of complex product hierarchies at the same time, also design of primitives to maintain the consistency. And the third one is zero allocation strategies. That is, we implemented a custom memory management to process CAD data without allocating new objects for each. This significantly reduced the garbage collection pressure and improved throughput by 85%. Now, next, let's talk about our event driven notification system built with Go channels. This system significantly improved the cross-stream communication. It works through four main steps. First one is every significant product data change generates events through a non-blocking channel-based system. This ensures that the producers never have to wait for consumer processing. Second, intelligent routing, central dispatcher route event based on payload that enables robust acknowledgement mechanism. And the last one, the final one is aggregated event streams, the real time, the real feed dashboards. This provides immediate visibility into process status. It reduces the cross-team communication delays by 45%. As our performance, we implemented a distributed caching architecture. This system uses multi-tier structure. We use in-memory cache backed by distributed radius clusters. Both efficient serialization enabled 80% faster data access across our services. We use prefetching. Machine learning model predicts likely data access patterns. It triggers background prefetching operation that populate the cache before request even arrives. To maintain data integrity, we have cache invalidation, a sophisticated publish subscribe mechanism that ensures cache coherence across the distributed nodes. Atomic operations prevent race conditions during the updates. And finally, the system uses adaptive sizing, memory allocation between the. Now, let's go to integrating AI into our PLM systems. It required advanced concurrency patterns. Proved to be very helpful here. We used custom sync primitives. We developed specialized synchronizing primitives that coordinate AI pipeline execution across distributed services while maintaining data consistency throughout the locking mechanism. We also implemented efficient memory pools, custom memory pools, pre-allocated buffers for large-scale data processing. It significantly reduced the garbage collection and enabled a stable performance even under the peak loads or log-free data structures, implementing atomic operations and carefully designed log-free data structures. It enabled us the concurrent access patterns and the linear scalability. These patterns were crucial for integrating machine learning. Now, let's talk about the GPRS. The efficient communication between our microservices is critical. We used GRPS for high performance communication. Our GRPS implementation is based on service definitions. We use strong type protocol for node generation directly from those interface definitions. GRPS supports directional streaming, enabling the efficient data transfer with multiplexed connection. It also provides client-side load balancing, and finally, it has performance monitoring with detailed metrics on. Let's talk about the that we implemented for the performance optimization. The first one is GC tuning. Then the second one is the back pressure mechanism, the context-based flow that prevented the system overload. And then the last one is the real-time monitoring we use for continuous profiling and to enable the automatic resource allocation. Our custom monitoring system leverage goes built-in profiling tools to provide real-time insights into the system, and it adjusted the resource allocation to maintain the optimal response times across all the services. The next one here is the real-time PLM transformation examples, an automated validation pipeline to identify and resolve the issues much earlier in the development process. The integration of machine learning model with our Go services enabled the predictive maintenance capabilities and reduced the system performance by our system downtime by 60%. Event-driven notification system improved the cross-team communication. And now the most important thing, the robust security and scalability architecture. For authentication and authorization, we implemented a service-to-service authentication using our TLS. We used rate throttling, and we used various data partitioning approaches here. Now, let's recap the key takeaways from the our business impact was significant: 30% faster product launch, 65% for technology implementation was centered around Go microservices, AI integration, and advanced concurrency. Architectural principles were focusing on event design, distributed caching, and efficient communication. And our journey demonstrates Go's elegant, a powerful foundation for